Okay, so we've got here, we've got symmetric equations. And we want to find, from that, we want to find a parameterization. We want to find symmetric equations for a different line achieved in the following way. We'll come back to that, right? And then we want to find a parameterization of that different line. Okay, so we're going to, grand total, we're going to end up with two different lines and two different parameterizations. Okay. Well, okay, so it's said differently. Two different symmetric equations for lines and two different parameterizations for, again, same lines. Okay, and then the last part is to conclude from this, we have these rules for, if you translate a solution set, how do you fiddle with an equation to result in a certain translation? We just want to figure out, if we're talking about parameterizations, what's the resulting thing? Okay, so first let's do the details. So step one, and we have these symmetric equations. Let's find the parameters.
Start a recording per chance?
I believe I did. I hope I did. Yes.
Okay.
Better to ask
Yes.
than to not have done it. Right. Okay. Right. Okay. So now, how do you find the parameterization? Don't forget the big trick on the relationship between symmetric equations and parameterizations is that the three objects in the symmetric equations are t. That's the trick. And then if you want to find the parameterizations, well, just solve for x, y, and z. Right. So this is straight out of the procedure in the book. So let's so solving for x. Well, I have x plus 1 is equal to t, therefore x is equal to negative 1 plus t. All right, now I have 2y minus 3 also equal to t, so y is t plus 3 all over 2. And then let's see, 3z plus 2 is equal to t. And solving for z, z is t minus 2 all over 3. Okay, everybody happy with that? And notice this is a parameterization. I mean, you can clean this up a little bit and write it as, let's do that over. Let me take this and move it over out of the way there. And so I can say x is negative 1, 3/2, negative 2/3 plus t times 1, 1/2, 1/3. Yeah, everybody good? Okay, so that is that's this first part. Okay, now, let's set that aside and question, how do we write the symmetric equations for, we're going to translate as indicated by the vector 1, 2, 3. So everything's going to move over by 1, 2, 3. So x is going to increase by 1. We want, I want all the points to move over by 1 in the x direction. I want them to move over by 2 in the y direction, etc. Yeah? Okay, well, we have tricks for that in equations. Now that this has served its purpose, let me get that out of the way so we don't use up too much space. But I am going to keep the parameterization here. Oh, by the way, this is for the line L. Okay, so 1, 2, 3. Well, I need these equations. Let me recopy these equations. X plus 1 equals 2y minus 3 equals 3z plus 2. And I want to adjust that to achieve this translation. Well, we have rules. And so in an equation, if you want all the x coordinates to increase by 1, you replace x with x minus 1. Right? So I'm going to end this algebra up here, I'm going to replace x with x minus 1. And then I'm also going to replace y with y minus 2 and z with z minus 3. Yeah, everybody good? And let's do that then. So I get, okay, x minus 1 plus 1 equals 2 y minus 2 minus 3 equals 3 z minus 3 plus 2. And notice all I did is follow my rules. X I replaced with x plus 1. Y I replaced with y minus 2. And z I replaced with z minus 3. Yeah? Happy? Okay. All right. Okay, now, and then let's go ahead and clean it up a little bit. So this becomes x equals 2y minus 7 equals 3z, whoops, z. Okay, minus 9 plus 2 makes minus 7. Okay. Okay, so there's, this is our L prime. Now, of course, Gesundheit. Did I call it L prime? Let's see, I think I called it L prime. Mm-hmm. Yeah. Okay. Okay, is everybody happy with that? Okay. All right, now again, I need some working space, so I'm going to delete a bunch of stuff here. I'm going to delete all of, oh, come on. Delete all of that. And let's move this up where I can use it later. You know what? I'm going to move this over to here, and this over to there. Okay. All right. All right. Next. Okay, let's parameterize L prime. Okay, well, same trick. So, I mean, this is just, you know, more details, but I've got to take this, set all three of these things equal to t, and solve, right? So, x is, 0 plus 1t. Y is t plus 7 all over 2. Z t plus 7 all over 3, which I can rewrite as x equals 0 7 halves, 7 thirds plus t 1 1/2 1/3. All right, everybody good? All right. Now, again, I'm going to clean up my mess a little bit. Erase these things, and what I have there is a parameterization of L prime. So this is L prime. And so now let me move that into a sensible place. Let's see here. Okay, well, I'm going to have to do a little shuffling. Get this over here out of the way. Let's put that up there, and then I'll move this underneath it. Okay. All right, everybody happy so far? Okay. Now, oh, you know what? The original line L, let's just for record purposes, let's write down its symmetric equations following the pattern below. X plus 1, 2y minus 3. 3z plus 2. Okay. Okay, so this is... Okay, so now on the left, this is our line L, parameterization and symmetric equations. On the right, we have L prime, parameterization, symmetric equations. All right, so we already understand how this happened. Right, that happened by everywhere you see an x, replace it with an x minus 1, etc. Right? So what I want to do, what this last part of the question is asking me to do, is to sort of, from the results that we've seen here, ask, how does this work? Right? If I want to translate a line, what seems to have happened in these parameterizations, and can I suspect a sort of a general rule from that? And so, well, there's an easy comparison to make. Notice that the direction vectors are the same. Right, that didn't change at all. So what about these base point vectors? How does that compare to that? What is that relationship? And notice the difference is, let me write this down with the yellow. In order to go this way, I add 1, 2, 3 to that base point. I hope my arithmetic is right. Yeah, 1, 2, 3. Does everybody see that?
Yeah.
Okay. Now, let's talk about why this is actually fairly plausible. This is one of these don't overthink it type situations, right? So with equations, then you can see how, okay, well, if I am adjusting the equations, what does that do to the solutions? And you can, there's this whole, undoing what you've done sort of point of view, and that's why everything's backwards, right? But don't forget what parameterizations are. Parameterizations are points. If you want to translate points such that the points have 1, 2, 3 added to them, how do you add 1, 2, 3 to a bunch of points? Well, you add 1, 2, 3 to the bunch of points. Right? Don't overthink it. This is exactly what you would hope would happen. Right? Now, I'm going to give you a different point of view on why this is not inconsistent. I mean, again, it sort of feels like, well, aren't we sort of making up different rules for different circumstances? And I claim not really. Because here's another way that you can think of a parameterization. Let's see, I'll do this in yet a different color. How about orange? A parameterization can be thought of as x equals, x naught plus tv. And so if I want to take this and, let's add 1, 2, 3. Let's translate by 1, 2, 3 by, okay, I'm going to add 1, 2, 3. Whoops. Notice I could instead interpret adding 1, 2, 3 to the actual points instead as x minus 1, 2, 3 equals x naught plus tv. So I could instead think of that as, I took this equation, and everywhere I saw in the equation, that's an equation, everywhere in the equation that I saw an x, I replaced it with x minus 1. And everywhere I saw a y, I replaced it with y minus 2. And everywhere I saw a z, I replaced it with z minus 3. So it's really the same procedure if you want to think of it that way. And it just manifests itself differently if you're interpreting your parameterization differently as just a bunch of points. Yeah? Is everybody happy with that? Okay. Any questions? Everybody good? Okay. All right.